We have mentioned activation energy before, so let's take a closer look at that and then also take a look at catalysts, as the two of them are very closely related. If we did a graph of an endothermic reaction, energy versus the course of the reaction, which would be the reaction coordinate, this is what that graph would look like. Note that the energy of the reactants would be lower than the energy of the products, which makes sense, as an endothermic reaction is a reaction in which energy is absorbed. Notice the activation energy is from the point of the reactants all the way to the very top of the energy of the reaction. So that's the energy needed to get the reaction going. And then notice here that the delta H, the enthalpy of the reaction, is the difference between the energy of the products and the energy of the reactants. An exothermic reaction, very similar in appearance. Again, energy on the y-axis, the course of the reaction over the x-axis. Notice that the energy of the reactants are higher in energy than the products. That's because, remember, in an exothermic reaction there is a loss of energy. Notice there the activation energy again is from the energy of the reactants to the very peak of the energy. And make note of the fact that the delta H again is the difference between the energy of the reactants and the energy of the products. Now, you can actually determine the activation energy using what is called the Arrhenius equation. The Arrhenius equation looks like what you see here on the screen. K is the rate constant at temperature T, so this is the K that we would calculate using the rate law. The A is the frequency factor, which is a constant specific for a reaction, and this particular value would be referenced. The E to the A, of course, is the activation energy, and then R is our gas constant. This is the Joule version gas constant, 8.31 joules per Kelvin moles. Now, if we rearrange the Arrhenius equation, we can turn it into a form, again, y equals mx plus b. We can simplify and solve for e to the a there. The negative e A, which is the activation energy, over the gas law constant, then is the slope when the reciprocal of the temperature is plotted against the natural log of K. The linear regression then of a table of reciprocal of temperature versus the natural log of K can then give us a slope. And the activation energy then is that slope value. Notice too in the equation that the natural log of A is the y-intercept. So you can actually take data, the reciprocal of temperatures and the natural log of K's at those temperatures, plot them, get the slope, and from the slope you therefore have the activation energy. Now, the word catalyst is important. It's a substance that speeds up a reaction without actually being consumed. Biologically, we call these catalysts enzymes. So an enzyme is a large macromolecule, usually a protein, that catalyzes biological reactions. Now, there are homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are present in the same phase as the reacting molecules. Heterogeneous catalysts are present in a different phase than the reacting molecules. Now, when a catalyst is utilized in a reaction, it literally takes that peak of the reaction that we saw in an earlier slide and it lowers it. Notice that the activated state without the catalyst is the solid sloped line, and then the dotted is the catalyzed energy reaction. And notice all it did was simply lower the hill there. Now an inhibitor would do the opposite. It would actually raise that above the activated state without the catalyst. Now, catalysts can function in a variety of different ways. One way is to increase the number of effective collisions. So note on the left there, the uncatalyzed, the blue area, the number of effective collisions. Notice on the right, same type of reaction, but it's been catalyzed, and notice the large yellow area, those are the effective collisions. So you get a greater number of effective collisions. Now, a heterogeneous catalyst, one example of how it would work, and this particular reaction involves carbon monoxide and nitrogen monoxide. The reactants absorb onto a surface, so platinum would be the catalyst, and platinum is going to come out of the reaction as platinum, but what it does is it provides a surface on which the reaction can actually take place. So the carbon monoxide and the nitrogen monoxide molecules absorb onto the platinum surface. They then arrange themselves on the surface so as to react, and then the carbon dioxide and nitrogen form from the molecules that you saw on the previous slide. So again, you get the molecules migrating to the surface, you get the molecules rearranging themselves on the surface so they're lined up and can react, and then step 3 here, you actually get the reaction happening, and then step 4, of course, is what you would think. The molecules are done reacting, so they are going to leave the platinum surface. So the platinum, again, it catalyzes this reaction without being consumed in the reaction.